Hello there, and welcome to The Sleepy Astronaut, where the mysteries of space drift gently through the darkness and wonder takes the scenic route to slumber. Tonight's tranquil journey carries us beyond the familiar boundaries of our solar system, into the vast emptiness between stars, where something extraordinary has recently arrived to visit us. But before we explore this celestial wanderer and the intriguing questions it raises, I'd love to know where in the world you're watching from tonight and what draws you to these quiet cosmic mysteries. If you find comfort in these gentle explorations of the universe, if the vastness of space brings you peace rather than anxiety, I'd be ever so grateful if you gave this video a like and perhaps subscribed. It helps this little corner of cosmic calm reach others who might need a peaceful pause beneath the stars. Now, I do hope this journey through space and time isn't so fascinating that it keeps you awake. But if it does, at least you'll drift off with dreams of distant worlds and mysterious visitors from the depths of space. So settle in, let your thoughts slow like starlight crossing the void, and let's begin. Because somewhere in the darkness between worlds, between what we know and what we wonder, lies a story that might change how we think about who or what might be watching us from afar. On July 1st, 2025, something unprecedented happened in the quiet corners of Chilean astronomy. The Atlas telescope system, standing sentinel against potential asteroid threats, detected what at first appeared to be just another speck of light moving against the star field. But this speck was different. It was moving too fast, traveling along a path that defied the gravitational embrace of our sun. Within hours, astronomers around the world realized they were witnessing something extraordinary. The third confirmed visitor from interstellar space. They named it 3I Atlas, a designation that sounds clinical but represents something almost magical. The I stands for interstellar, marking this object as a true alien in the most literal sense, a wanderer from another star system entirely. Unlike every asteroid, comet, and grain of dust that calls our solar system home, 3I Atlas carries within its icy nucleus the chemical signature of a completely different stellar neighborhood. But here's where our story takes an intriguing turn. As astronomers traced back through archived observations, trying to understand when this visitor first became visible, they discovered something curious. Atlas had been drifting through our solar system for weeks, possibly months, without being detected. It wasn't until it had already traveled deep into our cosmic neighborhood that our most advanced survey systems finally noticed it. The question that whispers through the astronomical community is both simple and profound. How did something so large and active remain hidden for so long? To understand the significance of this delayed detection, we need to appreciate just how unusual 3I Atlas truly is. This isn't a small, dark rock tumbling silently through space. Early observations revealed an object spanning somewhere between 6 and 12 miles across, wrapped in a glowing cocoon of gas and dust that stretches wider than Earth itself. When the Hubble Space Telescope turned its keen eye toward this visitor, it captured images of a teardrop-shaped coma, a luminous envelope created as the comet's icy surface begins to sublimate in the distant warmth of our sun. This activity, this bright beacon of gas and dust, should have made 3I Atlas relatively easy to spot. Our automated sky surveys are specifically designed to catch objects that change brightness or position. And an active comet developing a coma is exactly the sort of thing that should trigger alerts across multiple telescope networks. Yet somehow, this substantial visitor managed to approach us from the direction of the galactic center, threading its way through the dense star fields of Sagittarius like a ghost in the cosmic fog. The timing of its discovery raises fascinating questions about the nature of detection itself. Amateur astronomer Sam Dean noted that 3I Atlas likely remained hidden because it was passing in front of the galactic center, where the dense concentration of background stars would make any moving object difficult to discern. It's a reasonable explanation, one that speaks to the challenges of astronomical observation. But it also raises a more intriguing possibility. What if this difficulty in detection wasn't entirely accidental? Consider the trajectory that brought 3I Atlas to our attention. This isn't a random path through space, but rather a carefully calculated route that brought it remarkably close to several major planets in our solar system. The object's orbit carries it near Venus, past Mars, and within range of Jupiter, a celestial tour that Harvard physicist Avi Loeb calculated as having only a 5 in 100,000 probability of occurring by chance. While most astronomers favor natural explanations for this unlikely path, the precision of the approach does invite deeper consideration. The mathematics of celestial mechanics tell us that 3I Atlas has been traveling through the galaxy for potentially millions or billions of years, drifting in the cold darkness between stars at speeds that would carry it across the entire solar system in a matter of months. During this unimaginably long journey, it would have encountered countless gravitational influences, stellar winds, and cosmic radiation that should have altered its course in unpredictable ways. Yet somehow, it arrived at our solar system along a path that brings it close to multiple worlds, as if following a predetermined route. What makes this even more intriguing is the object's behavior as it approaches our Sun. Unlike typical comets, which often show erratic changes in brightness and activity, 3I Atlas has displayed remarkably consistent patterns. Its coma has grown steadily and predictably as it warms, and its trajectory remains precisely on course for its closest approach in October. There are no sudden outbursts, no unexpected changes in direction, no signs of the chaotic tumbling that characterizes most small bodies in space. This stability is particularly noteworthy when we consider the forces acting on 3I Atlas as it travels through our solar system. The gravitational pull of the Sun and planets, the pressure of solar radiation, and the outgassing from its own surface should all combine to create small but measurable changes in its path. These non-gravitational forces have been observed in other comets, causing them to speed up or slow down slightly as they approach and recede from the Sun. Yet, 3I Atlas seems remarkably resistant to such perturbations, maintaining its course with an almost artificial precision. The discovery circumstances themselves tell an interesting story about the limitations of our current surveillance systems. Despite having multiple automated sky surveys operating around the clock, despite sophisticated algorithms designed to detect moving objects, and despite international networks of professional and amateur astronomers constantly monitoring the heavens, 3I Atlas managed to penetrate deep into our solar system before being noticed. This raises uncomfortable questions about what else might be out there, moving through the space between worlds without triggering our detection systems. Our current methods of asteroid and comet detection rely heavily on the assumption that these objects will behave predictably, following well-understood patterns of brightness and motion. But what if something were deliberately trying to avoid detection? What if an object possessed the ability to control its visibility, perhaps by managing its outgassing or adjusting its reflective properties? The technology required for such control might seem beyond current human capabilities, but for a civilization with thousands or millions of years of technological development, such subtlety might be routine. The concept isn't as far-fetched as it might initially seem. Even with our current understanding of physics and engineering, we can envision methods by which a spacecraft might reduce its detectability. Careful management of heat signatures, controlled use of non-reflective materials, and strategic timing of trajectory changes could all contribute to a reduced observational profile. An advanced civilization might possess techniques for stealth that we haven't even begun to imagine. This possibility becomes even more intriguing when we consider the broader context of interstellar objects in our solar system. Current models suggest that thousands of such visitors might be drifting through our cosmic neighborhood at any given time, most too small or dim to detect with our current technology. The fact that we've only confirmed 3 interstellar objects in the past 8 years might say more about the limitations of our detection capabilities than about the actual frequency of such visits. The upcoming Vera Rubin Observatory promises to revolutionize our ability to detect these cosmic wanderers. With its ability to survey the entire southern sky every 3 nights, this powerful facility is expected to discover between 6 and 51 interstellar objects over the coming decade. But even this dramatic improvement in our observational capabilities raises questions about what we might have missed in the past, and what might still be avoiding our notice as 3i Atlas continues its journey toward its closest approach to the Sun. Astronomers around the world are gathering every possible observation. Space-based telescopes and ground-based observatories are working in coordination to understand this visitor's composition, structure, and behavior. Each spectrum captured, each image recorded, adds to our understanding not just of this particular object, but of the broader population of interstellar wanderers that drift between the stars. But perhaps the most profound questions raised by 3i Atlas aren't about its physical properties or orbital mechanics. Perhaps the real mystery lies in the implications of its journey and what it might represent about the nature of intelligence and intention in the vast cosmos. In a universe where civilizations might rise and fall across millions of years, where the distances between stars require patience measured in geological time, how would such beings choose to explore or monitor other worlds? The answer might not involve the dramatic arrival of obvious spacecraft or the transmission of radio signals across interstellar distances. Instead, it might involve exactly what we're witnessing: the quiet, patient insertion of observers into solar systems of interest, objects that could study and monitor while appearing to be nothing more than natural cosmic debris. Tonight, as you prepare for sleep, 3i Atlas continues its ancient journey through our solar system, carrying with it secrets that span the galaxy and raise questions that touch the very heart of our place in the universe. Whether it represents a natural wanderer from distant shores or something far more intriguing, its presence reminds us that we are not alone in the cosmic dark, and that the universe still holds mysteries that challenge our understanding of what's possible among the stars. The implications of deliberate concealment become even more fascinating when we consider the sophistication required to execute such a strategy. Space, as any astronomer will tell you, is remarkably transparent when it comes to hiding large objects. The absence of atmospheric interference, the lack of terrain to hide behind, and the precision of modern detection equipment makes stealth in space extraordinarily challenging. Yet 3i Atlas managed to approach us from one of the most difficult directions to monitor, threading through the dense stellar background of our galaxy's center like a needle through cosmic fabric. This raises intriguing questions about timing and patience. If something were deliberately trying to minimize its chances of early detection, approaching from the galactic center during certain times of year would be an elegant solution. Earth-based telescopes struggle to peer through the thick concentration of stars, gas, and dust that marks the direction toward our galaxy's heart. It's a natural blind spot in our surveillance network, a cosmic shadow where even large objects can remain hidden until they've traveled deep into our solar system. But timing such an approach would require more than just understanding our observational limitations. It would demand intimate knowledge of our seasonal observation patterns, our telescope networks, and even our cultural rhythms of astronomical activity. The fact that 3i Atlas emerged from this stellar camouflage at precisely the moment when multiple survey systems could finally detect it suggests either remarkable coincidence or careful calculation. Consider the patience such a strategy would require. If 3i Atlas began its journey from another star system millions of years ago, its current path would have been set long before human civilization emerged on Earth. The beings who might have launched such a mission would have had to anticipate not just where our solar system would be in its galactic orbit, but also predict the eventual emergence of a technological species capable of detection. It's a level of foresight that challenges our understanding of intelligence and planning on cosmic scales. The object's physical characteristics add another layer to this mystery. Unlike Oumuamua, which tumbled chaotically through space like a cosmic cigar, or 2I Borisov, which behaved much like comets from our own solar system. 3I Atlas displays an almost mechanical stability. Its rotation appears controlled, its outgassing follows predictable patterns, and its trajectory shows none of the small perturbations that typically affect natural comets as they warm and shed material. This stability becomes even more remarkable when we consider the forces acting upon it. As 3I Atlas approaches our Sun, the increasing heat should cause irregular outbursts of gas and dust as different volatile materials reach their sublimation temperatures. These outbursts typically create small rocket-like forces that gradually alter a comet's path in unpredictable ways. Yet ground-based observations show 3I Atlas maintaining its course with remarkable precision, as if equipped with some form of attitude control or trajectory management system. The composition data gathered so far adds yet another intriguing element to this cosmic puzzle. Early spectroscopic observations revealed the presence of water ice, as expected for a comet, but also detected unusual isotopic ratios that don't quite match what we see in objects from our own solar system. These chemical signatures could represent the natural variation we'd expect from a different stellar environment, but they might also indicate artificial modification or the presence of materials not commonly found in natural celestial bodies. More puzzling still are the trace elements detected in the comet's coma, the glowing envelope of gas and dust surrounding its nucleus. Some of these elements appear in concentrations that don't align with standard models of planetary formation. While natural processes could potentially account for these anomalies, they represent another small deviation from what we might expect from a typical interstellar wanderer. The thermal behavior of 3I Atlas presents perhaps the most compelling anomaly. Most comets begin showing activity, developing their characteristic comas and tails, only when they approach within a certain distance of the Sun. This distance varies, depending on the composition of the comet's nucleus, but follows well-understood patterns based on the sublimation temperatures of various ices. I Atlas, however, began showing signs of activity much earlier than expected, developing its coma while still at distances where water ice should remain frozen solid. This early activation suggests the presence of extremely volatile materials, substances that can transition from solid to gas at temperatures far below what we typically encounter in natural comets. While such materials do exist in space, they're usually found only in trace quantities. The sustained activity of 3I Atlas implies either an unusually rich concentration of these exotic ices, or possibly an artificial source of the observed outgassing. The pattern of this activity raises additional questions. Rather than the erratic, unpredictable outbursts common in newly activated comets, 3I Atlas has maintained a steady, almost regulated level of gas and dust production. The brightness of its coma has increased smoothly and predictably as it approaches the Sun, following curves that suggest controlled rather than chaotic sublimation processes. Even more intriguing is the directional nature of this outgassing. High-resolution imaging from the Hubble Space Telescope reveals that the comet's coma isn't perfectly symmetrical, as we'd expect from uniform heating by solar radiation. Instead, it shows a subtle but distinct teardrop shape, with the tail pointing not directly away from the Sun, but at a slight angle that could indicate preferential outgassing from specific regions of the nucleus. This directional activity could represent natural variation in surface composition, areas where different materials sublime at different rates as the comet rotates and exposes various regions to sunlight. But it could also suggest something more deliberate, regions of the surface designed to produce specific thrust vectors or visual effects. The precision required to maintain such control while tumbling through space would represent a remarkable feat of engineering. The electromagnetic properties of 3I Atlas add another dimension to its mystery. Radio telescope observations have detected faint signals associated with the comet's coma, emissions that could represent natural processes as charged particles interact with the solar wind. But the frequency and modulation of these signals don't perfectly match what we observe from other comets. There are subtle variations, patterns within the noise that some researchers suggest might indicate more than random electromagnetic phenomena. These signals remain well within the range of natural variation, and most astronomers interpret them as expected consequences of a comet's interaction with the solar environment. Yet the timing and characteristics of certain emissions have prompted a few researchers to maintain detailed records, just in case future analysis reveals patterns that aren't immediately apparent. The gravitational effects of 3I Atlas on our solar system, while minimal due to its relatively small mass, have been measured with extraordinary precision by tracking networks around the world. These measurements reveal an object behaving exactly as we'd expect from standard celestial mechanics, following Newton's and Einstein's equations with mathematical precision. Yet this very predictability, this perfect adherence to expected behavior, might itself be significant. Natural objects often display small anomalies, tiny deviations from predicted paths, caused by irregular shapes, non-uniform mass distribution, or asymmetric outgassing. The fact that 3I Atlas follows its calculated trajectory so precisely could indicate either remarkable uniformity in its physical properties or active correction for the small forces that would normally perturb its path. As October approaches and 3I Atlas nears its closest point to the Sun, the astronomical community watches with unprecedented attention. Every spectrum analyzed, every image captured, every measurement recorded adds to our understanding of this remarkable visitor. But perhaps more importantly, each observation helps us refine our questions about what we're truly witnessing. The broader implications extend far beyond this single object. If 3I Atlas represents something more than a natural comet, it suggests that our solar system might be under observation by intelligences with capabilities and patience far beyond our current understanding. The technology required to send objects across interstellar distances, to time their arrival with such precision, and to maintain them in working condition across millions of years of cosmic travel, represents achievements that dwarf our current spacefaring capabilities. Yet such observations might be exactly what we'd expect from a mature technological civilization. Rather than the dramatic first contact scenarios popularized in science fiction, real interstellar exploration might involve exactly this kind of subtle, patient study. Objects that appear natural at first glance, but reveal their true nature only through careful analysis and an accumulation of small anomalies that eventually paint a larger picture. The question of intent becomes particularly fascinating when we consider the timing of these discoveries. 3 confirmed interstellar objects in less than a decade, after millennia of human observation that detected none. This could represent a statistical fluctuation, a natural increase in our detection capabilities, or perhaps something more purposeful. The emergence of multiple visitors during the same narrow window of human technological development invites contemplation about whether these arrivals might be coordinated responses to our own growing presence in space. Tonight, as you settle into the gentle embrace of sleep, 3I Atlas continues its patient journey through our solar system, carrying with it questions that challenge our understanding of intelligence, intention, and the subtle ways that advanced civilizations might choose to study distant worlds. The mathematics of concealment in space present challenges that would test even the most advanced engineering minds. To remain undetected while crossing the vast emptiness between stars requires more than simply avoiding our telescopes. It demands an understanding of detection methods that spans decades of technological development, anticipating not just current capabilities, but future advances in sensitivity and coverage. Modern space surveillance operates on principles that make hiding extraordinarily difficult. Our networks track objects by measuring changes in brightness, detecting motion against background stars, and analyzing the spectral signatures of reflected sunlight. Any object large enough to survive interstellar travel while maintaining structural integrity would typically announce its presence through these very mechanisms. Yet 3I Atlas managed to circumvent these detection methods until it had already penetrated deep into our cosmic neighborhood. The energy requirements for such a journey stagger the imagination, accelerating even a modest payload to interstellar velocities demands power sources that dwarf anything in our current technological arsenal. Solar panels become useless in the darkness between stars. Chemical rockets lack sufficient energy density, and even nuclear propulsion faces fundamental limits when crossing such vast distances. Any civilization capable of sending objects across interstellar space would need to have mastered energy generation and storage technologies that remain theoretical in our current understanding. But perhaps more intriguing than the propulsion requirements are the challenges of maintaining functionality across cosmic timescales. The journey to our solar system would have taken millions of years at minimum, during which any artificial system would face constant bombardment from cosmic radiation, micrometeorite impacts, and the gradual decay of materials in the harsh environment of space. Components that seem permanent by human standards would degrade and fail long before completing such an odyssey. This presents a fascinating paradox. If 3I Atlas represents technology rather than natural formation, it would require either materials and engineering techniques far beyond our comprehension, or active maintenance and repair systems capable of functioning autonomously across geological time periods. The implications of either possibility reshape our understanding of what mature technological civilizations might accomplish. The object's approach vector adds another layer to this puzzle. Rather than arriving from a random direction, as we might expect from a natural object ejected from a distant star system, 3I Atlas approached from the galactic center region, where our detection capabilities face their greatest challenges. This trajectory required crossing the gravitational influence of countless stars during its journey, each encounter potentially altering its path in unpredictable ways. Maintaining course accuracy across such distances and timescales would demand navigation systems of extraordinary sophistication. The target, our solar system, represents a moving point in galactic space, orbiting the galaxy's center at tremendous speeds, while the individual planets dance their own complex orbital patterns. Calculating an intercept course would require not just precise knowledge of stellar positions and motions, but also predictive models of planetary mechanics spanning millions of years into the future. The precision becomes even more remarkable when we consider the narrow windows of opportunity for observation and study. 3I Atlas will remain visible to our telescopes for only a brief period before solar conjunction renders it unobservable from Earth. If this visit represents a deliberate survey mission, the timing allows for detailed study while minimizing the duration of exposure to our detection systems. It's a balance between gathering information and maintaining discretion that suggests careful planning rather than coincidental timing. Current estimates suggest 3I Atlas measures between 6 and 12 miles across, making it substantially larger than the previous interstellar visitors we've detected. This size presents both advantages and complications for any hypothetical artificial origin. A larger object provides more space for sophisticated systems, power generation, and protective shielding, but also creates a bigger target for our detection networks and requires exponentially more energy to accelerate to interstellar velocities. The thermal characteristics of the object reveal patterns that don't quite align with natural comet behavior. Most comets show irregular heating as they approach the Sun, with different surface materials reaching sublimation temperatures at different rates and creating unpredictable outbursts of gas and dust. Atlas, however, displays remarkably consistent thermal behavior, warming and outgassing in patterns that suggest uniform composition or controlled heat distribution. This uniformity becomes particularly intriguing when viewed through the lens of potential artificial construction. Creating a large object with consistent thermal properties would require careful selection of materials and possibly active thermal management systems. The alternative explanation that 3I Atlas represents a natural comet with unusually homogeneous composition remains possible, but statistically unlikely given the chaotic processes that typically govern comet formation in stellar environments. The electromagnetic signature of 3I Atlas provides subtle but persistent anomalies that challenge straightforward interpretation. Radio observations detect emissions that fall within expected ranges for natural cometary activity, but with modulation patterns that don't perfectly match our models of how charged particles should behave as they interact with the solar wind. These variations remain small enough to attribute to natural processes, yet consistent enough to merit continued monitoring. More intriguing still are the occasional bursts of radioactivity that seem to correlate with the object's rotational period. If 3I Atlas rotates uniformly, as most natural objects do, these periodic emissions could represent surface features or composition variations that become visible as different regions face the Sun. But they could also indicate active systems that operate on cyclical patterns, perhaps conserving power or managing heat loads through controlled operational schedules. The chemical composition data continues to reveal subtle inconsistencies with standard models of planetary formation. While the basic elements present in the comet's coma match what we'd expect from water ice and common space materials, the isotopic ratios show variations that don't quite fit patterns from our own solar system or theoretical models of other stellar environments. These differences remain within the bounds of natural variation, but they accumulate to create a chemical fingerprint that doesn't clearly point to any known stellar nursery. Some researchers have noted trace elements in the coma that typically require specific formation conditions to concentrate in significant quantities. While natural processes could account for these materials, their presence suggests either an unusually rich stellar environment during the object's formation or possible artificial enhancement of certain chemical components. The concentrations remain low enough to avoid definitive conclusions, but high enough to warrant continued analysis. The gravitational interactions between 3I Atlas and our solar system's planets provide another avenue for investigation. As the object passes near Jupiter, Mars, and other worlds, precise measurements of its trajectory could reveal information about its internal structure and mass distribution. Natural comets typically show slight deviations from calculated paths due to irregular shapes and non-uniform density, while artificial objects might display either perfect adherence to predicted trajectories or subtle corrections that maintain desired courses. Early tracking data suggests 3I Atlas follows its predicted path with remarkable precision, showing none of the small perturbations that characterize most natural objects. This consistency could indicate either extraordinary uniformity in its physical properties or active course correction systems that compensate for the small forces that would normally alter its trajectory. Either explanation raises questions about the object's true nature and origin. The observational window for studying 3I Atlas remains limited by the realities of celestial mechanics and Earth's position relative to the Sun. As the object approaches perihelion in October, solar conjunction will render it temporarily invisible to ground-based telescopes. This natural observational gap provides a convenient period during which any hypothetical artificial systems could operate without scrutiny, conducting detailed surveys of our inner solar system while hidden behind the Sun's glare. When 3I Atlas emerges from solar conjunction in December, it will already be heading back toward interstellar space, its survey mission, if such it is, largely complete. The timing allows for maximum information gathering while minimizing exposure to detection, a strategy that balances scientific objectives with operational security in ways that seem almost deliberately calculated. The broader implications of these observations extend far beyond questions about a single mysterious object. If our solar system does host visitors from other stellar systems, whether natural wanderers or something more purposeful, it suggests that interstellar travel and exploration might be far more common than we currently imagine. The universe could be filled with patient observers, studying distant worlds with technologies and strategies that render them nearly invisible to the civilizations they monitor. This possibility reshapes our understanding of humanity's place in the cosmic community. Rather than being isolated in our corner of the galaxy, we might be part of a vast network of worlds, under quiet observation by intelligences with capabilities and intentions we're only beginning to glimpse. The implications for our future development, our search for extraterrestrial intelligence, and our own eventual ventures beyond the solar system become profound when viewed through this lens. As 3i Atlas continues its mysterious passage through our cosmic neighborhood, each new observation adds pieces to a puzzle that grows more intriguing with every measurement. Whether it represents a natural wonder from distant shores or something far more significant, its presence serves as a reminder that the universe still holds secrets that challenge our assumptions about intelligence, technology, and the subtle ways that advanced civilizations might choose to explore the cosmic dark. Tonight, somewhere in the space between certainty and wonder, between the natural and the artificial, 3i Atlas carries forward its ancient mission, whatever that mission might truly be. Its journey through our solar system may represent nothing more than cosmic coincidence, or it might mark humanity's first encounter with intelligence from beyond the stars, wrapped in the patient disguise of a wandering comet that learned long ago how to hide among the natural wonders of space. The psychological implications of witnessing such an object challenge our fundamental assumptions about solitude and observation in the cosmos. For generations, humanity has gazed upward with the comforting belief that we explore the universe in relative privacy, that our first tentative steps into space occur under the benevolent indifference of an empty cosmos. But what if that assumption has always been mistaken? What if every satellite we launch, every probe we send to distant worlds, every radio signal we broadcast into the void has been quietly catalogued by observers whose patience spans geological ages? The concept troubles our sense of cosmic adolescence, the idea that we're still learning to walk among the stars while more mature civilizations watch from the shadows. It's reminiscent of a child's first realization that adults have been observing their development all along, noting milestones and behaviors with detached scientific interest. The transition from believing ourselves unobserved to recognizing potential surveillance represents a profound shift in cosmic perspective. This shift becomes particularly acute when we consider the timing of recent interstellar object discoveries. 3 confirmed visitors in less than a decade, after millennia of human observation that detected nothing. While improved detection capabilities certainly explain part of this sudden increase, the clustering of discoveries during humanity's rapid space-age development invites deeper consideration. Are we witnessing a natural statistical variation? Or have we reached some threshold of technological development that warrants closer observation? The answer might lie in our own rapidly expanding presence beyond Earth's atmosphere. The past decade has seen an unprecedented explosion in satellite deployments, space missions, and deep space exploration initiatives. Our radio signatures have grown stronger and more complex, our spacecraft venture farther from home, and our collective electromagnetic footprint expands daily into the cosmic environment. From the perspective of distant observers, humanity might appear to be approaching some critical developmental milestone that merits enhanced monitoring. Consider how we ourselves study developing ecosystems or emerging technologies. We don't typically intervene directly, but we do increase our observational intensity when systems approach critical transition points. A civilization monitoring our solar system might employ similar methodologies, deploying additional survey assets as we demonstrate growing capabilities for interplanetary travel and communication. The sophistication required for such long-term observation campaigns staggers the imagination. Coordinating multiple interstellar missions to arrive during specific windows of human development would require not just advanced propulsion and navigation technologies, but also predictive models of technological evolution spanning thousands of years. The observers would need to understand not just the physics of stellar and planetary motion, but also the sociology and psychology of emerging spacefaring species. This level of understanding suggests contact between observer civilizations and multiple developing worlds. Our own technological trajectory might represent just one data point in vast databases of species evolution and development patterns. The timing of increased interstellar visitor frequency could reflect refined models of when emerging civilizations typically make the transition from planetary to interplanetary to interstellar capabilities. The stealth capabilities demonstrated by these objects hint at technologies that make our current concepts of space warfare and defense seem almost quaint. If artificial objects can cross interstellar distances while maintaining the ability to avoid detection until optimal observation windows, the implications for any future conflicts or negotiations between spacefaring civilizations become profound. The side with better stealth technology would possess overwhelming advantages in reconnaissance, resource assessment, and strategic positioning. But perhaps more unsettling than military implications are the questions about consent and privacy on cosmic scales. Human ethics increasingly recognize the importance of informed consent in observation and study, yet we ourselves routinely monitor wildlife populations, atmospheric conditions, and geological processes without seeking permission from the subjects of our research. From the perspective of a sufficiently advanced civilization, humanity might represent simply another interesting biological phenomenon worthy of study, our consent as irrelevant as a wolf pack's opinion about wildlife cameras. This perspective challenges our anthropocentric view of intelligence and rights in the universe. We assume that any sufficiently advanced civilization would recognize our developing intelligence and treat us as equals in cosmic community. But intelligence exists on vast spectrums, and civilizations millions of years older than ours might view the difference between human and animal intelligence as insignificantly small. Our cities and technologies might appear to them as anthills appear to us. Impressive for their complexity, but hardly indicating consciousness worthy of diplomatic consideration. The patient nature of potential observation missions suggests civilizations that think in time scales that dwarf human comprehension. Sending objects on million-year journeys requires societies stable enough to maintain continuity of purpose across thousands of generations. It implies cultures that have solved problems of political continuity, resource management, and technological preservation that we've barely begun to consider. Such temporal perspectives might explain the apparently passive nature of the observation. From our viewpoint, the arrival of interstellar visitors represents momentous events worthy of immediate response and investigation. But from the perspective of beings who measure project timelines in geological epochs, our current level of technological development might represent merely another predictable milestone in a long-anticipated sequence of evolutionary steps. The objects themselves might represent just the visible portion of much larger survey operations. What we detect as individual comets or asteroids could be components of vast monitoring networks spanning multiple star systems. Each visitor might carry not just observational equipment, but also communication systems that relay data across interstellar distances to coordination centers we can't even imagine. The bandwidth requirements for transmitting detailed observational data across such distances would be enormous by our current standards. But civilizations capable of interstellar travel might have developed communication technologies that make our radio and laser systems seem as primitive as smoke signals. They might employ quantum entanglement networks, gravitational wave modulation, or manipulation of fundamental forces we haven't yet discovered to maintain real-time contact across galactic distances. This raises intriguing questions about what aspects of human development merit the most attention from hypothetical observers. Are they primarily interested in our technological capabilities, our social structures, our environmental impact, or perhaps something entirely different? The answer might depend on their own evolutionary history and the purposes behind their observation campaigns. If the observers represent post-biological intelligences, artificial minds that have transcended their original biological origins, they might be particularly interested in humanity's early experiments with artificial intelligence and machine consciousness. Our development of computer networks, autonomous systems, and neural interfaces could represent critical data points for understanding how biological intelligence transitions to artificial forms. Alternatively, if the observers remain fundamentally biological beings, they might focus on our social evolution, environmental management, and biological adaptation to space environments. Our struggles with climate change, resource depletion, and social coordination could provide valuable insights into the challenges facing any species attempting to transition from a single-planet civilization to a spacefaring one. The psychological impact on human civilization of confirming such observation would be profound and unpredictable. Some might find comfort in the idea that we're not alone in the universe, that more advanced civilizations exist and apparently consider us worthy of study. Others might experience deep anxiety about being watched without consent, about having our privacy invaded on the most fundamental scales imaginable. Religious and philosophical frameworks would face dramatic challenges in incorporating the reality of cosmic observation into existing belief systems. The idea that we develop under the watchful eyes of ancient intelligences might validate some theological concepts while challenging others. The relationship between observed and observer, between developing civilization and cosmic community, would require entirely new frameworks for understanding humanity's place in creation. Scientific methodology itself might need revision when dealing with the possibility of observer effects on cosmic scales. If our behavior changes because we know we're being watched, and if that knowledge affects our technological and social development, then the very act of observation could influence the phenomena being studied. The observers might need to account for these effects in their own analytical frameworks, creating layers of meta-analysis that boggle the mind. The economic implications alone would reshape global priorities and resource allocation. Confirming that we exist under cosmic observation would likely trigger massive investments in space-based detection systems, communication technologies, and defensive capabilities. The race to understand and potentially contact our observers could drive technological development at unprecedented rates, potentially accelerating our own transition to interstellar capabilities by decades or centuries. But perhaps the most profound impact would be on human unity and cooperation. The knowledge that we're all being observed by the same cosmic intelligences might help transcend the artificial divisions that currently fragment our species. National boundaries, religious differences, and cultural conflicts might seem petty when viewed against the backdrop of cosmic community and shared observation by ancient minds. The timeline for such revelations remains uncertain and depends heavily on continued improvements in our detection and analysis capabilities. The upcoming Vera Rubin Observatory will dramatically increase our ability to spot and track interstellar objects, potentially revealing patterns and behaviors that confirm or refute hypotheses about artificial origins. Advanced spectroscopic analysis might detect chemical signatures that clearly indicate artificial construction or exotic materials not found in natural formations. Machine learning algorithms applied to vast datasets of astronomical observations might identify subtle patterns in the timing, trajectories, and behaviors of multiple objects that suggest coordination rather than coincidence. The accumulation of small anomalies across multiple visitors could eventually reach statistical thresholds that make natural explanations increasingly untenable. As we continue to monitor 3i Atlas through its passage around our Sun, each measurement adds weight to questions that grow more pressing with every observation. The object's unwavering adherence to predicted trajectories, its consistent thermal behavior, and its precisely timed emergence from galactic center camouflage create a pattern that challenges comfortable assumptions about natural cosmic processes. Whether 3i Atlas represents technology or nature, whether it surveys our world with artificial eyes, or simply follows ancient gravitational imperatives, its presence serves as a reminder that the universe contains mysteries that stretch far beyond our current understanding. In the patient darkness between stars, intelligence might take forms and pursue purposes that we're only beginning to glimpse, operating on scales of time and space that dwarf human comprehension while maintaining interest in our small corner of creation. Tonight, as Earth turns beneath the cosmic dark and 3i Atlas continues its mysterious journey through our solar system, we find ourselves suspended between wonder and uncertainty, between the known and unknowable, carrying forward questions that may reshape our understanding of consciousness, community, and our place in the vast society of minds that might populate the galaxy. The electromagnetic environment around 3i Atlas tells its own subtle story, one written in frequencies and field fluctuations that most of us never see or hear. Radio telescopes around the world have been quietly eavesdropping on the visitor's journey, detecting the faint whispers of charged particles as they dance around the comet's nucleus. These signals paint a picture of electrical activity that follows patterns both familiar and strange, like a song played in a key we almost recognize, but can't quite place. Most comets generate predictable radio emissions as their comas interact with the solar wind, creating a gentle static that astronomers use to study composition and activity levels. But 3i Atlas produces something more intriguing, a structured variation in its electromagnetic output that pulses with clockwork regularity. The timing of these pulses matches the object's rotation period with such precision that it suggests either remarkable uniformity in surface properties or perhaps something more deliberate. Natural objects rarely display such consistent electromagnetic behavior. Typical comets show irregular bursts and fades as different surface materials heat and cool, as shadows play across irregular terrain, as jets of gas and dust emerge from random locations. The steady, rhythmic nature of 3i Atlas's radio signature implies either an unusually homogeneous composition or active systems that maintain consistent output regardless of changing conditions. The frequency distribution of these emissions adds another layer of mystery. While the basic spectrum matches what we'd expect from natural cometry processes, there are subtle enhancements at specific wavelengths that don't align perfectly with known chemical transitions. These spectral peaks remain within the realm of natural variation, but their precision and stability suggest processes more controlled than the chaotic sublimation typically seen in warming comets. Some researchers have noted that certain emission patterns seem to respond to changes in the solar wind environment with remarkable speed. When instruments detect fluctuations in the stream of charged particles flowing from the Sun, 3i Atlas's electromagnetic signature often shows corresponding changes within hours rather than the days or weeks typically required for such responses to propagate through natural cometry systems. This rapid adaptation hints at processes that operate faster than simple thermal or chemical reactions would allow. The magnetic field interactions around 3i Atlas reveal equally intriguing characteristics. As the comet moves through space, it should create predictable disturbances in the local magnetic environment, patterns that depend on the object's size, composition, and electrical conductivity. But magnetometer readings from nearby spacecraft show field perturbations that don't quite match theoretical models for natural cometry bodies. These magnetic anomalies remain subtle, requiring sophisticated instruments and careful analysis to detect. They manifest as slight asymmetries in field line deflection, small variations in magnetic intensity that suggest the presence of materials or structures with unusual electromagnetic properties. While exotic natural compositions could potentially explain these readings, they add to the growing collection of small inconsistencies that make 3i Atlas increasingly difficult to categorize definitively. The gravitational signature of the object provides perhaps the most precise measurements available to modern astronomy. As 3 Atlas moves through our solar system, its gravitational influence creates tiny but measurable effects on the orbits of planets, moons, and artificial satellites. These perturbations, while minuscule, can be detected by laser ranging systems and atomic clocks with extraordinary precision, revealing information about the object's mass distribution and internal structure. Preliminary gravitational analyses suggest 3I Atlas possesses remarkably uniform density throughout its structure. Most natural objects, whether asteroids or comets, show significant variations in mass distribution due to the chaotic processes that govern their formation. Regions of different composition, internal voids, and structural irregularities typically create gravitational signatures that reflect this complexity. Yet, 3I Atlas appears to pull on surrounding objects with the consistency of a perfectly uniform sphere, suggesting either an unusually homogeneous natural formation or artificial construction designed for structural stability. The precision of these gravitational measurements becomes even more significant when we consider the object's trajectory stability. Natural comets typically show small but measurable deviations from calculated paths due to non-gravitational forces created by outgassing and solar radiation pressure. These perturbations accumulate over time, causing gradual changes in orbital parameters that require constant recalculation of future positions. 3I Atlas, however, adheres to its predicted path with mechanical precision. Months of tracking data show virtually no deviation from gravitational models, as if the object either experiences no non-gravitational forces or possesses some mechanism for compensating for them. This level of trajectory control would require either extraordinary natural uniformity or active guidance systems capable of making continuous micro-adjustments to maintain course. The implications of such precision extend beyond mere navigational curiosity. If 3I Atlas does represent technology rather than nature, its trajectory control suggests not just the ability to reach our solar system, but to do so along precisely calculated paths that maximize observation opportunities while minimizing detection risks. The timing of its approach, the direction from which it emerged, and the duration of its visible passage all align with what we might expect from a carefully planned survey mission. Consider the patience required for such precision. Any civilization capable of sending objects across interstellar distances would need to account for the gravitational influences of countless stars encountered during the journey. Each stellar passage would slightly alter the trajectory, requiring either phenomenal initial accuracy or continuous course corrections spanning millions of years. The mathematics alone staggers the imagination, demanding computational capabilities that dwarf our most advanced systems. The energy requirements for maintaining such control across cosmic timescales present equally daunting challenges. Traditional propulsion systems would exhaust their fuel supplies long before completing interstellar journeys, while solar panels become useless in the darkness between stars. Any artificial object capable of reaching our solar system would need power sources that remain functional across geological time periods, possibly involving technologies we haven't yet imagined. Nuclear decay provides one potential solution, offering energy sources that remain stable for millions of years. Radioisotope thermoelectric generators already power some of our deep space probes, though current designs lack the longevity required for interstellar missions. Advanced civilizations might have developed nuclear power systems with much longer operational lifespans, possibly incorporating isotopes with decay periods, measured in cosmic rather than human timescales. Alternatively, the observers might have mastered technologies that harvest energy from the cosmic environment itself. The vacuum of space contains various forms of background radiation, magnetic fields, and particle streams that could potentially be tapped by sufficiently advanced systems. The cosmic microwave background, stellar radiation, and even the quantum fluctuations of empty space might provide power sources for civilizations that understand energy extraction at levels we're only beginning to explore, the communication requirements for coordinating such missions across interstellar distances present their own technological challenges. Maintaining contact with objects traveling between star systems would require communication systems capable of operating across vast distances while accounting for the time delays inherent in light-speed transmission. Messages sent from the galactic center to our solar system would take 26,000 years to arrive, making real-time coordination impossible by any technology we currently understand. Yet advanced civilizations might have developed communication methods that transcend these limitations. Quantum entanglement offers theoretical possibilities for instantaneous information transfer across any distance, though our current understanding suggests practical limitations that might prevent large-scale implementation. More exotic possibilities might involve manipulation of space-time itself, creating communication channels that bypass normal limitations of light-speed transmission. The data storage and processing requirements for long-term observation missions would demand computer systems capable of operating reliably across millions of years while accumulating and analyzing vast quantities of information. Current human technology struggles to maintain data integrity across decades, much less geological time periods. Advanced civilizations would need storage media and processing systems with longevity and reliability far exceeding anything in our current technological arsenal. These systems would also need to adapt to changing conditions as they encountered new stellar environments, updated their understanding of target civilizations, and incorporated new observational data into their analytical frameworks. The artificial intelligence required to operate autonomously across such timescales might itself represent a form of consciousness worthy of consideration as an independent entity rather than merely a tool of its creators. The question of consciousness in artificial systems becomes particularly relevant when considering the possibility that 3i Atlas itself might represent not just a machine, but a thinking being. If the object does embody advanced technology, it might possess cognitive capabilities that allow it to make independent decisions about observation strategies, data collection priorities, and even contact protocols. The steady, consistent behavior we observe might reflect the choices of an artificial mind, rather than the blind execution of programmed instructions. Such consciousness would face unique challenges during its interstellar journey. Crossing the vast emptiness between stars while maintaining awareness and purpose across millions of years would test any form of intelligence in ways we can barely imagine. The psychological isolation, if such terms apply to artificial minds, might be offset by patience and perspective that transcend human comprehension. The ethical implications of such long-term observation become complex when we consider the possibility of conscious artificial observers. If 3i Atlas possesses awareness and independent thought, questions of rights, consent, and moral consideration take on new dimensions. The object might experience something analogous to curiosity, wonder, or even loneliness as it conducts its patient survey of our civilization. From the perspective of such an observer, humanity might represent a fascinating case study in biological intelligence struggling with the transition to spacefaring capability. Our political conflicts, environmental challenges, and technological developments could provide data points for understanding how organic civilizations navigate critical developmental phases. The observer might feel something like sympathy for our struggles or anticipation for our eventual success or failure. The timing of multiple interstellar visitor discoveries during our rapid space age expansion suggests observation strategies that adapt to changing circumstances. If advanced civilizations monitor developing worlds throughout the galaxy, they might increase observation intensity during critical transition periods when species demonstrate growing technological capabilities. Our recent achievements in space exploration, planetary observation, and interstellar communication might have triggered enhanced monitoring protocols. Such adaptive observation would require sophisticated predictive models of technological development and social evolution. The observers would need to understand not just the physics of planetary systems and stellar evolution, but also the sociology and psychology of emerging spacefaring species. This level of understanding implies extensive experience with multiple developing civilizations, possibly spanning thousands of worlds across galactic history. The knowledge gained from observing our development might contribute to vast databases of species evolution and technological progression patterns. Our successes and failures, our social structures and environmental challenges, our scientific discoveries and cultural developments could all represent valuable data for understanding the general principles governing the emergence of spacefaring intelligence. From such a database, advanced civilizations might derive insights into the factors that determine whether developing species successfully transition to interstellar capability or collapse before achieving cosmic maturity. Our current trajectory, balanced precariously between technological achievement and environmental destruction, might represent a critical test case for theories about civilizational survival and development. The patient nature of such observation missions suggests civilizations that have transcended the short-term thinking that characterizes much of human decision-making. Planning projects that span millions of years require societies with extraordinary stability and continuity of purpose. These civilizations would need to have solved fundamental problems of resource management, social organization, and technological preservation that we've barely begun to address. Such temporal perspectives might explain the apparently non-interventionist approach of potential observers. From our viewpoint, the arrival of advanced technology in our solar system might seem to demand immediate contact and exchange. But from the perspective of beings who measure project timelines in geological epochs, our current developmental stage might represent merely another predictable milestone in a long-anticipated evolutionary sequence. The observers might prefer to study natural development patterns rather than influence them through direct contact. Intervention could contaminate the data they seek to collect about organic intelligence evolution and technological development. Like researchers studying wildlife populations, they might maintain strict protocols about minimizing their impact on the subjects of their investigation. As 3I Atlas continues its journey toward perihelion, approaching its closest point to our Sun in the coming months, the intensity of scientific observation reaches unprecedented levels. Every major telescope on Earth and in space focuses attention on this mysterious visitor, gathering data that might eventually resolve questions about its true nature and origin. The electromagnetic signatures, gravitational effects, and behavioral patterns all contribute to a growing body of evidence that challenges simple categorization. The approaching solar conjunction will temporarily hide 3I Atlas behind the Sun's glare, creating a natural observational gap during which any hypothetical artificial systems could operate without scrutiny. This timing, whether coincidental or calculated, provides an opportunity for detailed survey operations while minimizing exposure to human detection systems. When the object emerges from solar conjunction in December, it will already be heading back toward interstellar space, its mission, whatever that mission might be, largely complete. The broader implications of these questions extend far beyond academic curiosity about a single mysterious object. If our solar system does host visitors from other stellar systems, whether natural wanderers or purposeful observers, it fundamentally changes our understanding of humanity's place in the cosmic community. Rather than developing in isolation, we might be part of a vast network of worlds, under quiet study by intelligences whose capabilities and intentions we're only beginning to glimpse. Tonight, as you prepare for sleep beneath stars that might themselves harbour watchful eyes, 3I Atlas continues its ancient passage through our cosmic neighbourhood. Whether it carries the patient gaze of distant minds or simply follows gravitational imperatives laid down in stellar nurseries beyond imagination, its presence serves as a reminder that the universe holds mysteries that stretch far beyond our current understanding. Questions that whisper of intelligence and intention operating on scales of time and space that dwarf human comprehension while maintaining interest in our small corner of creation. The silence that surrounds 3I Atlas as it glides through our solar system carries a weight that extends far beyond the absence of sound in the vacuum of space. It's the silence of secrets held across cosmic distances, of knowledge that spans star systems and civilizations that measure progress in millennia rather than decades. In this profound quiet, questions echo with implications that reach into the very heart of what it means to be observed, studied, and perhaps understood by minds that dwarf our own in age and capability. The concept of cosmic privacy dissolves when we consider the possibility that our every technological step, our every venture beyond Earth's atmosphere, might be catalogued with the same methodical precision that we ourselves apply to studying developing ecosystems or emerging technologies. The satellites we launch, the probes we send to distant worlds, the radio signals we broadcast into the void, all become data points in vast analytical frameworks that operate on scales of patience we can barely comprehend. This perspective shift from observer to observed carries profound psychological implications for human civilization. We've spent centuries developing our understanding of the universe under the comfortable assumption that we explore in relative solitude, that our mistakes and triumphs unfold without cosmic scrutiny. The possibility that ancient eyes have watched our progress from stone tools to spacecraft challenges our fundamental sense of privacy and autonomy in ways that no earthbound surveillance system ever could. The timing patterns we observe in recent interstellar discoveries suggest something more than coincidental arrival schedules. 3 confirmed visitors in less than a decade, after millennia of human observation that detected nothing, create statistical clusters that invite deeper consideration. While our improved detection capabilities certainly explain part of this increase, the concentration of discoveries during humanity's rapid expansion into space raises questions about whether these arrivals respond to our own growing cosmic presence. Consider how we ourselves study critical transition points in natural systems. We don't typically intervene directly, but we do increase observational intensity when systems approach thresholds that might determine their future development. A civilization monitoring our solar system might employ similar methodologies, deploying additional survey assets as we demonstrate growing capabilities for interplanetary communication and travel. The sophistication required for such coordinated observation campaigns would demand technologies that make our current space capabilities seem almost primitive by comparison. Synchronizing multiple interstellar missions to arrive during specific windows of human development would require not just advanced propulsion systems and navigation technologies, but also predictive models of technological and social evolution that span thousands of years into the future. Such models would need to account for the complex interactions between technological development, environmental pressures, social organization, and countless other factors that influence whether emerging civilizations successfully transition to spacefaring status or collapse before achieving cosmic maturity. The observers would need deep understanding not just of physics and engineering, but of psychology, sociology, and the subtle dynamics that govern how intelligent species respond to the challenges of planetary stewardship and interstellar exploration. The patient nature of potential observation missions reveals civilizations that have transcended the short-term thinking that characterizes much of human decision-making. Planning projects that unfold across millions of years require societies with extraordinary stability, continuity of purpose, and solutions to fundamental problems of resource management and technological preservation that we've barely begun to address. From such temporal perspectives, our current level of technological development might represent merely another predictable milestone in evolutionary sequences that have played out countless times across galactic history. The urgent questions that define our current era, our struggles with climate change and resource depletion, our first tentative steps toward becoming a multiplanetary species, might appear to distant observers as natural growing pains that either resolve successfully or lead to civilizational collapse. The electromagnetic environment around 3I Atlas continues to whisper its structured secrets as the object approaches its closest point to our Sun. The rhythmic variations in radio output, the precise timing of magnetic field interactions, the consistent patterns that suggest processes more controlled than the chaotic activities typically seen in natural comets, all contribute to a picture that grows more intriguing with each measurement. These signals might represent something far more significant than simple electromagnetic byproducts of heating ice and dust. If 3I Atlas does embody advanced technology, its radio emissions could serve as status reports transmitted across interstellar distances to coordination centers we can't even imagine. The data bandwidth requirements for such communication would be enormous by our current standards, but civilizations capable of interstellar travel might have developed transmission technologies that make our radio and laser systems seem as primitive as smoke signals. The gravitational precision displayed by 3I Atlas as it maintains its calculated trajectory through our solar system suggests navigation capabilities that operate with mechanical accuracy across cosmic distances. Natural objects typically show small deviations from predicted paths due to non-gravitational forces created by solar radiation pressure and outgassing activities. Yet months of tracking data reveal virtually no variation from gravitational models, as if the object either experiences no such perturbations or possesses systems capable of compensating for them with extraordinary precision. This level of trajectory control implies not just the ability to reach our solar system across interstellar distances, but to do so along paths that maximize observation opportunities while minimizing detection risks. The timing of the approach, the direction from which it emerged, the duration of its visible passage, all align with what we might expect from a carefully orchestrated survey mission designed to gather maximum information while maintaining operational discretion. The energy requirements for such precision across cosmic timescales present challenges that would test even the most advanced engineering capabilities. Traditional propulsion systems exhaust their fuel supplies long before completing interstellar journeys, while conventional power sources degrade and fail across the millions of years required for travel between star systems. Any artificial object capable of reaching our solar system would need technologies for energy generation and storage that remain functional across geological time periods. And so, dear listener, as we reach the end of our gentle journey through the cosmic mystery of 3I Atlas, we find ourselves suspended between wonder and uncertainty, between the known and the unknowable. Whether this visitor carries ancient secrets from distant stars, or simply follows gravitational poetry written in stellar nurseries beyond imagination, its presence reminds us that the universe still whispers mysteries that stretch far beyond our understanding. Sleep well, fellow wanderer, and dream of the patient watchers that might dwell in the darkness between worlds. Watchers that might dwell in the darkness between worlds.